If successful scientific theories can be thought of as cures for stubborn problems, quantum physics was the wonder drug of 20th century. It successfully explained phenomena such as radioactivity and antimatter, and no other theory can match its description of how light and particles behave on small scales. But it can also be mind-bending. Quantum objects can exist in multiple states and places at the same time, requiring a mystery of statistics to describe them.
Rife with uncertainty and riddled with paradoxes, the theory has been criticized for casting doubt on the notion of an objective reality, a concept many physicists, including Albert Einstein, have found hard to swallow. Today, scientists are grappling with these philosophical conundrums, trying to harness quantum's bizarre properties to advance technology and struggle to weave quantum physics and general relativity in seamless theory of quantum gravity. Quantum theory began to take shape in the early 20th century when classical ideas failed to explain some observations. Previous theories allowed atoms to vibrate at any frequencies, leading to incorrect predictions that they could radiate infinite amounts of energy, a problem known as ultraviolet catastrophe. In 1900, Max Planck solved this problem by assuming atoms can vibrate only at specific or quantized frequencies. Then in 1905, Einstein cracked the mystery of photoelectric effect, whereby light falling on the metal releases electrons of specific energies. The existing theory of light as waves failed to explain the effect, but Einstein provided a neat solution by suggesting light came in discrete packages of energy called photons, a brain wave that won him the Nobel Prize of Physics in 1921. In fact, light's chameleon-like ability to behave either a particle or a wave depending on the experimental setup has long stymied scientists.
One controversial experiment recently challenged this either-or scenario of light by apparently detecting evidence of both wave and particle-like behavior simultaneously.
The work suggests there may be no such thing as photons. Light appears quantized only because the way it interacts with matter. For about 70 years, this wave-particle duality was explained by another unsettling tenet of quantum theory, the Heisenberg's uncertainty principle. Formulated by Werner Heisenberg in 1927 and recently made more precise, the theory puts an upper limit on the knowledge. It says one can never know both the position and momentum of a quantum object. Measuring one invariably changes the other. But more recent work suggests the underlying cause of duality seen in experiments is a phenomena called entanglement. Entanglement is the idea that in quantum world objects are not independent if they have interacted with each other or come into being through the same process. They become linked or entangled such that challenging one invariably affects the other, no matter how far apart they are. Something Einstein called spooky action at a distance. This may be involved in superconductivity and may even explain why objects have mass. It also holds promise for teleporting particles across vast distances, assuming everyone agrees on a reference frame. The first teleportation of quantum state occurred in 1998, and scientists have been gradually entangling more and more particles, different kind of particles and large particles. Entanglement may also provide nearly an uncrackable method of communication. Quantum cryptographers can send key to decode encrypted information using quantum particles. Any attempt to intercept the particle would disturb their quantum state and interference that could be detected. In April 2004, Austrian financial institution performed the first money transfer encrypted by quantum keys, and in June, the first encrypted computer network with more than 2 nodes was set up across 10 kilometers in Cambridge, Massachusetts and US. But keeping quantum particles entangled is a tricky business. Researchers are working on how to maximize the particle signal and distance traveled. Using a sensitive photon detector, researchers in UK recently sent an encrypted photon down to the length of 100-kilometer fiber optic cable. Researchers of US devised a scheme to entangle successive clouds of atoms in the hopes of one day making a quantum link between US cities of Washington, D.C. and New York. Quantum computers are another long-term goal because quantum particles can exist in multiple states at the same time. They could be used to carry out many calculations at once, factoring a 300-digit number in just seconds compared to the years required by conventional computers. But to maintain their multi-state nature, particles must remain isolated long enough to carry out the calculations. A very challenging condition. Nonetheless, some progress has been made in this area. A trio of electrons, the building blocks of classical computers, were entangled in semiconductors in 2003, and the first quantum calculation was made with a single calcium ion in 2002. In October 2004, the first quantum memory component was built from a string of cesium ions. But particles of matter interact so easily with the others that their quantum states are preserved for a very short time, just billions of a second. Photons, on the other hand, maintain their state about 1,000,000 times longer because they are less prone to interact with each other. But they are also hard to store as they travel literally at the speed of light. In 2001, scientists managed to stop the light in its tracks, overcoming one practical hurdle. And the first site of quantum logic gate, the brains behind the quantum computers, was created with light in 2003. While 3 of the 4 fundamental forces of nature, those operating on very small scales, are well accounted for by the quantum theory, gravity is in its Achilles heel. This force works on a much larger scale, and quantum theory has been powerless so far to explain it. A number of bizarre theories have been proposed to bridge this gap, many of which suggest that the very fabric of space-time bubbles up with the random quantum fluctuations, a form of wormholes and infinitesimal black holes. Such a form is thought to have filled the universe during the Big Bang, dimpling space-time so that structures such as stars and galaxies could later take shape. One recent theory, called doubly special relativity, tweaks Einstein's idea of one cosmic invariant. The speed of light adds one another at very small scales. The controversial theory accounts for gravity, inflation, and dark energy. Physicists are now devising observations and experiments that could test the competing theories. Quantum physics is usually thought to act on light and particles smaller than molecules. Some researchers believe that there must be some cutoff point where classical physics takes over, such as the point where the weak pull of gravity overwhelms other forces. In fact, gravity's effect on neutrons was recently measured. But macroscopic objects can obey quantum rules if they don't get entangled. Certainly, harnessing troops of atoms or photons that follow quantum laws holds great technological promise. Recent works cooling atoms to nearly absolute zero have produced new forms of matter called Bose-Einstein and fermionic condensates. These have been used to create laser beams made of atoms that etch precise patterns on surface, and might one day lead to superconductors that work at room temperatures. All of these hopes suggest that as queasy as quantum can be, it remains likely to be the most powerful scientific cure, all for the years to come. I'm always fascinated by quantum mechanics, how quantum particles defy the rules of classical physics. I hope I was successful in creating that for you too. If I was, do drop a like. And don't forget to put your suggestion in the comments down below. And I'll see you on the next one. Until then, keep it real.